Markandeya, for giving me opportunity to give a lecture on this in this platform. So my today's topic is triple diffusive convection with gravity modulation. So all of you know that fluid mechanics, already you might have heard about this. It's a fluid mechanics is a very important branch of science and engineering. It is related to the behavior of fluids, that is liquid and gases, which is either at rest or in motion. So starting from the day activity, opening the tap water, switching off fan, sitting in a AC room, our breathing, all this involves the application of fluid mechanics. So we see that application of fluid mechanics in every activity we come across in our daily life. So this is a very important topic to learn about. What are the recent applications or recent research happening in the fluid mechanics. And the very important one in fluid mechanics is heat transfer. So heat transfer is one of the most important application in fluid mechanics. And there are three modes of heat transfer. One is conduction, convection, and radiation. Among all these three, convection is the most dominant and efficient way of heat transfer here. So we deal here with a convection problems. So let me, before we go to the triple diffusive convection, we'll see what are the important types of single and double convection here. So we have very important one is the Rayleigh-Bénard convection. So it is the Bénard who gave the experimental and Rayleigh gave the theoretical treatment to that, the Bénard's experiment here. So what is this Rayleigh-Bénard convection? So we take in a fluid, fluid between the two parallel plates separated by a distance d here, and separated by a distance d. So, and we heat the fluid from below here. We are heating the fluid from below and the gravity acts vertically downwards. So when we heat the fluid from below, the convection will not start immediately because the temperature difference between the lower and upper plate, it is not strong enough to overcome the viscosity and thermal conductivity of the fluid here. As we keep heating the fluid, at one particular temperature difference between upper and lower plate, the convection sets in here. So it will be like this here. The convection sets in. And what is the physical mechanism for this convection? So when we heat the fluid, the fluid particle which are at the bottom layer will get heated up and they move towards the upper plate, and they become, because upper plate we are cooling here, they loses the heat, they become heavier and they move downwards here. So this upgoing and downcoming fluid particles will release a potential energy which gives the kinetic energy for the motion of the fluid. Okay, so this is how the Rayleigh-Bénard convection take place. Okay, so this is first, as I said earlier, it is theoretically treatment was given by Lord Rayleigh and explored mathematically in many straightforward but experimentally difficult cases. One of them is stress-free boundaries at top and bottom, which is not possible to analyze in the experimental case. And he uses the he used the Buznovskian approximation to make the fluid as incompressible. So this analysis set a path for further analysis here. And it is summarized in the chapter 1 of the Chandrasekhar's book, Hydrodynamic and Stability of Hydrodynamics and Hydromagnetics here. So as I said, at one particular point at one particular point of temperature difference, the convection sets in here. And this temperature difference in non-dimensional form is measured by using the Rayleigh number R here. Okay, it is used by using the Rayleigh number R, and we define that Rayleigh number as the ratio of destabilizing effect of buoyancy to the stabilizing effect of viscosity. So this system will be stable. That means when you take this, the temperature difference at which the convection sets in, we call it as a critical Rayleigh number. If the Rayleigh number is less than the critical Rayleigh number, there is no motion of the fluid particles there. But there is a transfer of heat from lower plate to upper plate here. And this is due to convection here. So the convection takes place when Rayleigh number R is greater than or equal to critical Rayleigh number. That means the system becomes unstable. And sometimes this the critical Rayleigh number also depends upon the type of boundaries we use here. We use sometimes both the boundaries may be a rigid boundary, both are free boundary, or one rigid and one free boundaries also. So when we talk about the Bénard convection, we can have different components of Bénard. What I explained you till now is a single component. Okay, so there are two components and three components of convection here. It is not only just with three components. Actually, there are multi-component convection also. To understand that better understanding of multi-component convection, we need to have we are using the triple diffusive convection here. Okay, so let me just see that. So before we go to that, let us see what is diffusion. So diffusion is a non-mechanically driven mixing process. It occurs when the fluids in which there are gradients of two or more different properties and with different molecular diffusivity here. Okay, this phenomena is of great interest to many disciplines in physical science and engineering here. And the first person to study this diffusion is the Turner. So we have a standard Bénard problem where that it is caused due to the temperature difference between the upper and lower plate, and this in literature is termed as single component convection. In addition to this temperature, if you add a solute, that means there are two opposing density with differing molecular diffusivity. We call this as two component convection. When we say two component, convection is induced either by temperature and concentration difference, or it may be a concentration difference of two species. Okay, and this has attracted many interesting phenomena, and especially this double diffusive convection is very important in the case of the study of oceanography, where we have heat, the sunlight, and the salt from the seawater, and this leads to a different types of double diffusive convection here. So what are the types of double diffusive convection? Okay, so let us see here. So there are four different cases we get. Let us take the case one, where we are heating the fluid from below and we are salting from above here. So when we heat the fluid from below, as I already told you, the fluid particles become lighter and they move towards the upper plate. So what happens here in this case here, it disturbs the entire system. Similarly, when you add the solute from the top plate, so because the solute particles are a little denser, that's heavier particle, they move towards the lower plate here. So when we heat fluid from the fluid from below and solute from above, so both this heat and solute, it destabilizes the system. It makes the system unstable here. So we find that both are destabilizing and system becomes unstable. Similarly, when you take the next case here, suppose if you heat from above and solute from below. So what happened in this case here, when you heat from above, so all the fluid particles in the above, near the upper plate will become less dense, and they stay there only near the upper plate. And when you solute from below, all these fluid particles will get settled down at the bottom. So there is no movement of fluid particles when we heat from above and solute from below. So both heat and solute will not disturb the system. They make the system stable. And we are not interested in these two cases here, because without solving the problem, the first case is always remain unstable, and the second case it becomes stable here. So there is no point in studying this type of these cases here. So we take another case, the third case, where we heat from above and salt from above. What happens in this case? When we heat from above, it stabilizes because all the fluid particle, because of that, it remains here. But the solute, whatever we add, it moves towards the down. So one is stabilizing, the other one is destabilizing here. This case, when we heat this, you can see that this fluid particles, when it moves from upper to lower plate, because there is a heat at the upper plate, there is a solute, and this solute absorbs the heat, and they move towards the lower plate, and they form a finger-like structure. And this we call it as the salt fingering here. This is in literature we call it as salt fingers here. So this is one of the important case, because the one component is stabilizing, the another component is destabilizing. Heat is stabilizing, adding the solute is destabilizing. So this is one of the interesting component, because interesting case, because we don't know what happens as time passes, whether the system remains stable or unstable. Similarly, we have the fourth case. The fourth case, what we are doing, we are adding the heat from, we are heating from below and adding the solute from below. So what happened in this case here, when we do this, we know that the temperature destabilizes, disturb the system, destabilizes, but the solute settles at the bottom and it stabilizes here. Here also, one component is stabilizing, the another component is destabilizing. So when this one salty water moves upward, because it becomes lighter, the salty water moves upward, so it becomes cold water when it reaches the upper plate here. And these water molecules are driven back with greater force, and this is termed as overstability, and this leads to a growing oscillations here. So these two cases, case 3, the actual case 4, we call it as a diffusive convection. So the third case is salt fingering, and diffusive convection is very important to study this. So when we talk about the double diffusive convection, there exist 4 cases in which the third and fourth cases are very important to study here. Okay, now let me come to the triple diffusive convection here, which is my main topic here. So what we observed here is, in many examples of double diffusive phenomena, density depends not only on heat and 2 component, it depends upon more than 2 or even 3 or more components here. In literature, such a convection, we call it as a multi-component convection. As I told earlier, the first step in understanding the multi-component convection is the triple diffusive convection. And so what happens here, when the double diffusive convection, we have only 2 agents. One is, we are considering it may be heat, and one is concentration of salts, or it may be both of them are concentration here. But when we add the third component to the system, either from bottom or from the top layer, then we find that what I explained earlier, the finger interface and diffusive interface, even the finger interface may become a diffusive interface, or diffusive interface may become the finger interface. Okay, so this is a very important results what we get when we have a triple diffusive convection. And there are so many important type of results we can observe in triple diffusive, which is not observed in the double diffusive convection. And this triple diffusive convection, it has got application in astrophysics, the astrophysics, atmospheric science, and the transport of groundwater flow, acid rain effects, etc. In so many cases where we have more than 2 components, the triple diffusive convection will come into the exist. I already explained you the different types of double diffusive convection. Like that, we can have different types of triple diffusive convection. So we have only 4 types of double diffusive convection, but when it comes to triple diffusive convection, there are 8 types of triple diffusive convection we come across here. Okay, so like depending upon whether we heat from above or below, we salt one solute from the above or below, or second one from above or below, depending upon the different cases, we'll have 8 different cases. So in this problem, what I'm going to discuss with you, I'm going to consider the triple diffusive case of the last one, the 8th case here, where we are heating from below, and both the solutes we are adding from below. This is the case. And what about the other cases? From this result, I'll explain you from this result, heating that last case, even I can get the results of almost all the cases, the other remaining 7 cases result from this, the study itself here. Okay. So let me see what is that convictions we have. So let me just, yeah. So another important concept, I think you can see this PPT, no? There's no problem with that. Sir Shripad, sir.
Fine, sir. No issues.
Modulations. Okay. So we have this another important concept. What I consider in this problem is modulation. So what is modulation? It is a process of fluctuating one or more characteristics of the periodic waveform, because the convection always sets in the waveform. Okay, it's theoretical. It's proved that. So when the convection sets in, it will sets in the waveform. So we can use the different concepts of the modulations. And the modulations, when we talk about the modulation, so the modulation, it depends upon the frequency of waveform, the amplitude, and even the phase angle between them here. So and the first person to use this modulation is the Donnelly. So in his experimental, okay, in 1964, so when he is experimenting the flow of fluid between the two cylindrical thing, he used this modulation term here. So, and then motivated by his work, so many people, Venezian is the next person who used theoretically this, the modulation of modulations in the different formats here. Okay, so it is one of the, and it is come to that the external modulation of the stability is the very important, that is one of the effective ways of controlling the convection here. So we use here the gravity modulation. Generally, we take gravity as a constant, but here we are considering gravity as it's a time dependent here. Okay, so we can see this the thermogravitical variation, we call them as the G jitter or the gravity modulations here. Sometimes it is also called as time periodic body force. And the gravity modulation we consider, suppose if there is no modulation, so epsilon becomes 0, amplitude becomes 0, you get G equal to minus G naught into K cap, and which is nothing but a constant one here. But here what we are considering here is, so we are considering G as minus G naught into 1 plus epsilon F into gamma T into K cap here, where G we are considering is a function of time here, where epsilon is the amplitude of modulation, gamma is the frequency of modulation, and this F of gamma comma T. We use here different types of modulation, sinusoidal and non-sinusoidal type of modulation. So we use this F either sinusoidal or non-sinusoidal waveforms here. Okay, so we use this F can be either sinusoidal or non-sinusoidal. When we talk about the sinusoidal modulation, so it is generally we consider as a trigonometric wave function. Either it is, we can take that as a sine or cosine. And non-sinusoidal modulation, we'll have 3 types of non-sinusoidal modulation. One is triangular waveform, square, and sawtooth. So this is a sine modulation, the sine wave. And similarly, we take this as the square wave modulation. We use that definition of F, and all these are obtained by using the Fourier series. So this expression for A0, AN, BN, and F we obtain by using the Fourier series expression here. So this is the expression we use for A0, AN, BN for our F for square wave, and we use triangular wave by using this expression. So again, as I said, we calculate by using the Fourier series. And the sawtooth waveform, so it is, we use this as a expression here. So in our problem, we used all the 4 types, that is sinusoidal, that is sine, we use cosine here, and then we have non-sinusoidal, triangular, sawtooth, and square, and we made a comparative study with this here. And not only we use the comparative study of this, but also at the end we considered some of the aqueous solution, a known aqueous solution, and we also use the triple diffusive convection to study that the stability of this mixture of the aqueous solutions. So let me come to that part later here. So, and recently in 2019, the Siddheshwar and Kanchana, they used this, the influence of trigonometric sine, square and triangular waveform to study the gravity aligned oscillation in a Rayleigh-Bénard convection in Newtonian liquids. So we take the physical configuration. So physical configuration consists of the two parallel plates in the vertical direction separated by a distance d, z equal to 0, z equal to d. And since you can observe that lower plate we have t equal to t naught plus delta t, S1 equal to S1 naught plus delta S1, S2 equal to S2 naught plus delta S2. So T represents the temperature, that is the heating. S1 and S2 are the two solutes, and we can observe that we are heating from the below because the temperature at the lower plate is more than the temperature at the upper plate. Similarly, the solute concentrations are both the solute concentrations are more at the lower plate compared to upper plate, which means that we are heating from below and then soluting from below here. And this is a gravity, which is a time periodic gravity, which we call it as G jitter or gravity modulations. And these are the governing equations we consider to solve this problem. Well, equation 1 represents the conservation of mass. Equation 2 represents the conservation of linear momentum, where we consider G as a gravity which depends upon the frequency and time. And the conservation of energy is given by this expression, equation number 3. And conservation of solutes, we are combine the two equations. If I put I equal to 1, you get S1 like that, and that will represent the conservation of solutes in the first solute. And when you put I equal to 2, you get the conservation of this in the second solute. And then equation of state we are using here. So this gives the how the density varies with temperature and the solutes. Again, we are using equal to 1 to 2 summation you can use. And in this, all the quantities Q represents here the velocity, rho naught is the density at constant temperature, P is the pressure, and we call dou Q by dou T as the local acceleration. This Q dot del Q is the convective acceleration, rho G here. This is where we use that Bosnowskian approximation. What is that? The Bosnowskian approximation states that the density remain constant throughout this linear momentum equation, except in a term it is multiplied with gravity. So this rho G we call it as a buoyancy force, and this is a viscous force. Okay, and G we are considered as I explained earlier. And here T is the temperature, P is the diffusivity of temperature, and then S1 and S2 are the solutes, and the solutes diffusivity alpha T, alpha S1 or alpha T is the coefficient of thermal expansion, coefficient of solute expansions. And then so we follow this. I'm not going to do in detail about the procedure. So what we do here is to solve this problem, we make use of the procedure of the stability analysis. So first we analyze this with the basic state, which I skipped here, and then we take that as we disturb the basic state. We disturb the basic state by adding a little perturbation. So all these prime quantities will denote the perturbation, and whatever we are the first terms, all those things will represent the basic state solution here. And what we do when we solve this problem, we have so many variables here. In order to reduce the number of variables, we consider only two-dimensional flow. One is horizontal and the vertical. Horizontal is x direction, vertical is the z direction. So in order to reduce the number of terms, we use a stream function, which is defined by u equal to dou psi by dou z, w equal to minus dou psi by dou x. And we use this stream function, we consider this stream function in such a way that they satisfies the continuity equation, conservation of mass. So and also what we do by substituting this, we also make this, once if you substitute this, we also make this equation, all the equations as dimensionless here. This is a very important concept in fluid mechanics, because when you take any of those equations, each term will be represented with a different physical, different units. Okay, if you take the linear momentum equation, we have pressure term, viscosity term, buoyancy term, and acceleration terms in the left. Each one will have a different units. So in order to compare each one term with the other one, we make the entire equation as dimensionless here. Okay, so we have a dimensionless quantities here, where this PR, 1 by PR represents the Prandtl number, RA is the Rayleigh number, RS1, RS2 are the solute Rayleigh number of solutal Rayleigh number, RS1 for first one and first solute, second solute, and epsilon is the, as I explained already, it's the amplitude, and then we have tau 1, it is called as diffusivity ratio, tau I, actually I equal to 1 and 2, tau 1 and tau 2, which we call as the diffusivity ratio. And to solve this problem, we need a boundary conditions. We assume that the boundaries are stress free. That is what it gives, psi equal to del square, psi equal to 0. And also we take that the temperature is the isothermal temperature and also iso concentration here. So this is what we at z equal to 0 and 1, lower boundary and upper boundary. So this is the boundary condition we use to solve this system of equation. So what we do here in the first case here, so we have 3 equation. We are combining all these 3, actually not 3 equation, it is a 4 equation when you take I equal to 1 and 2. So we combined all these 4 equations in terms of psi by eliminating theta, phi s1 and phi s2. So when we do that, we get a single equation in terms of psi. And you can observe that when I substitute for x1, x2, x3, x4 here, this becomes a 10th order equation here. So since it's a 10th order equation, we need 10 boundary conditions to solve this equation 12. And these boundary conditions are given by equation number 13. We have 5 boundary conditions: psi, dou square psi, delta to the power of 4, dou to the power of 6, dou to the power of 8. 5 boundary conditions at z equal to 0, 5 boundary conditions at z equal to 1. So we get 10 boundary conditions to solve this equation here. Okay. So then what we do the next is, we apply a perturbation method to solve this equation. What we do in perturbation method, so we know that RA is the one which we have to find, that we call it as a eigenvalue, and the corresponding value of psi, the eigenvector we call. We expand both these by in terms of a series in terms of amplitude epsilon here. So we take RA as RA naught into psi naught plus epsilon into RA1 psi 1. We expand this here, where RA naught represent, you can see that the coefficient, that RA naught coefficient is epsilon to the power of 0, which represent there is no modulation here. So this RA naught represents the Rayleigh number for no modulation case, and RA1 and RA2, they represent the corrections to this corrections to this Rayleigh number. So we are finding in the case of modulation thing, for an unmodulated case, we find the corrections to this here. So what we do here is, the mathematical procedure is, we take this equation number 14 and substitute in equation number 12. When I substitute that, I get in terms of epsilon, epsilon square, etc. I equate both sides with the coefficients of epsilon to the power of 0, epsilon, epsilon square. I get different equations here. The first equation, L of psi naught equal to 0, which is obtained by equating the coefficients of epsilon to the power of 0. And second equation, that is equation number 16 by epsilon to the power of 1. Equation 17, epsilon to the power of 2, where L, what we define, it is given by this expression here. So then we follow here the Venezian approach. I'm not giving the details of this. So when I solve this by Venezian approach, I get the following expression here. I get RA naught. It is given by RS1 by tau 1 plus RS2 by tau 2, k to the power of 6 by pi square a square. Now look at this. This is the Rayleigh number what we get. So when we use the for this triple diffusive convection here. Suppose if you put RS1, RS2 0 here. When we put RS1, RS2 0, so we get only k to the power of 6 by pi square a square. This is the expression for Rayleigh number for a single component here. If you take, and this is the classical Rayleigh expression, Rayleigh-Benard expression here. Suppose if I put RS2 0, Now I have only two components. So that is K to the power of 6, this single component. RS1 is one of the solute. So I get an expression for RA for for a double diffusive convection. And with RS2, we get the expression for triple diffusive convection. So from this, I can obtain the results of the single component, double component, as well as triple component. So when we use a Venetian approach, we get RA1 will become equal to 0, and RA2, the correction to the Rayleigh number, we get up to there. And we have calculated only up to epsilon square. If one requires the higher order, this one, you can just calculate, the further you can calculate, the RA3 will again become 0. You can find RA4, like that we can continue with it. We stop this stage itself here. Okay, so RA0 is the unmodulated Rayleigh number, RA2 is the correction to that unmodulated Rayleigh number. So now where that expressions are given by this, and now we take that as explained earlier, we calculate this RA2 with this difference. So where we get this in A, if you take A, we have F double dash, F dash, and F whole square here, and these are all the things which we use this, we to evaluate this, we use F here. F is given, as I said, we use sinusoidal, that is a cosine modulation here. So we substitute F as cos omega t, we evaluate that, we get a Rayleigh number for correction, Rayleigh number for cosine modulation. Similarly, for other three modulations, we get this here. Okay, and similarly what we do, this is what we consider here, this expression for RA0, RA2 is for the linear case. There are two analysis we do usually when we take this fluid mechanics. One is especially the convection problem. One is the linear analysis, where we take only linear equation and solve, and non-linear analysis. So linear stability analysis gives the condition for the onset of convection, but it will not explain the heat and mass transfer. If you want to study heat and mass transfer, we have to go for the non-linear stability analysis. So what we do, we expand this psi theta phi s1 phi s2 by truncated Fourier series. In this problem, we are used the higher mode truncated series. So usually the studies will occur for the only with A1, A2, B1, B2, C1, C2, C3, but we added the higher modes to get a more accurate the heat and mass transfer here. Okay, so what we do here is we take this IT and SI1, SI2, we substitute in that expression, in the basic expression, and by simplifying that, we get this 11 equation. We call this as the Lorentz system, 11 mode Lorentz system here, and we solve this 11 modes Lorentz system by using this numerical methods and Mathematica here. Okay, so here we can get all these expressions are defined. In this case, if you put x2, y2, y3, z2, z3, u1, u2, all these things, if you put 0, we get a classical Lorentz equation which is defined for the standard Rayleigh problem. So our interest in this, the nonlinear analysis to study the heat and mass transfer. This heat and mass transfer are, it is quantified by Nusselt number, the heat transfer, and we have SHI tau. That means there are two, because we have two solutes, we have to find what is the mass transfer of these two solutes here. So we define this as Sherwood numbers here. And also, since we have a modulation here, we talk about the mean Nusselt. We calculated the mean Nusselt. There's an average Nusselt number, average Sherwood number by using 39,940 here. So when we plotted this graphs, we plotted the graph for a very small amplitude, and here it is very important. I told you in the earlier that 8 cases of triple diffusive convections are there. So that all depends upon what is the values we give for RS1 and RS2 here. Okay, so if you give RS1, RS2 both positive values, then it indicates it stabilizes. Stabilizes means what? It is we are saluting from below. And if RS1, RS2, if you give negative value, it destabilizes. That means we are saluting from above. So by taking a different values for RS1, RS2, positive, negative values, I can get the results of all the 8 types of the triple diffusive convection. I'll just explain few of them here. This is the plot what we plotted for R2C versus omega, and the case 1 what we have taken is RS1 positive, RS2 positive. That means both the solutes are added from below. Case 2, when you take, we have RS1 positive, RS2 negative. That means the one solute 1 is added from below, solute 2 is added from above here. So like that, by giving it different values for RS1, RS2, we can calculate, we can get all the results. So what the first result states here, when you have this, you can observe this solid line is for 50 and the dotted line is for 75. So if you increase the concentration of the solute 1, where I have taken RS2 is also positive here, we can see that it stabilizes the system. As R2C increases, it stabilizes the system. Similarly, when you take the second case, RS1 is stabilizing, that is you are adding from below, RS2 is from above. In this case also we see that it stabilizes the system. As the RS1 increases, the R2C is also increasing. But when you take the third case, where we take RS1, that is the first solute from above, second solute from below, that's the third component, you can see that now the result, it is reverse here. Okay, so when you increase this RS1, it decreases the RS2, it destabilizes the system, it makes the system more unstable. Like that, if you take both of them from the above, we get the system will be the stabilizing, destabilizing here. Okay, so we can get all those results from this. I'll skip some of the results because of the time constraint, because sir asked me to complete by 10:30. These are the results what we got. Now R2C is for this T is for triangular. We have 4 types, different types. We have taken non-sinusoidal and sinusoidal. What happens? Only 3 results we got, because triangular and sawtooth, they coincides in this problem here. So therefore, we observe that from the figure, the R2C of T represents the triangular waveform, C for cosine, S for square. So we observe that the system is more stable in the case of square wave and less stable in the case of triangular wave. So what all they explain? The second result gives here epsilon equal to 0 means no modulation, and epsilon not equal to 0 is with modulation. The Rayleigh number is, that is, the system becomes more stable when we have with modulation here. Like that, the different cases, the results what we obtained here, and these are the results for heat and mass transfer. I'll explain this at the end. So we observe that these are the different graphs what we plotted, and we observe that Nu, SH1, SH2, it increases with RS1 and RS2. Whatever the case we take, it is from above or below, so it increases. The Nusselt number, that is, a Nusselt number increases means the heat transfer will increase, mass transfer also increase when you increase the concentration of solute 1 and 2. Similarly, we observe that the heat transfer is less in the case of square waveform and more in the case of cosine waveform. Same thing, we observe that the mass transfer, both the mass transfer are less in the square waveform and more in the cosine form. And as diffusivity ratios, if you see, the heat and mass transfer will decrease with the increase in the diffusivity ratio. But when you take again the other type, that is when you take with tau2, the third component what we are adding, so we get a reverse effect with respect to tau2 here. So this I told you in the beginning. We also calculated, we did some, we took some real solutes, that is aqueous solution, and we also calculated the things, and we observed that here these are the 4 different combinations we have taken: water plus NaCl, BaCl2, KCl and BaCl2. These are the different combinations of the triple diffusive convection aqueous solution, real aqueous solutions we have taken, and we calculated the RC for all this thing and R2C, and we observed that the R2C will increase with it will increase for the highest what we get for KCl and BaCl2, and the lowest one what we get highest is for KCl and NaCl, and the lowest one we get it for NaCl, CaCl2. That means KCl plus NaCl2 is the most stabilizing one, the other one is the destabilizing one. So this is what we get here, the results of that. And here also we observe that the square is the maximum, and like that. And even we calculated the heat and mass transfer for all this aqueous solution. So we got the results like this, that is more in KCl and CaCl2. Heat transfer is more when you can take the combination of the aqueous solution of KCl and CaCl2, and very less in the case of NaCl and BaCl2. Similar results what we explained in the other one we have. So these are the results what we have here. So we have results of, in comparison with results of no modulation, all types of gravity modulation increases the critical number, thereby decreases the Nusselt number and shear input. That decreases the heat and mass transfer. Square modulation is the most stabilizing, and sawtooth is the most destabilizing. And then we have the effects of, we observe that sawtooth and triangular, it remains identical. So what we observed that having just a water in the base fluid may not, system may be inadequate in some situation. So there is a need for using a aqueous solution in it. So this is the results what we obtained earlier, and these are some of the references which I have considered here. So this is what my lecture here. So thank you very much for patience listening. Sir Shripad sir.
Yes, sir. For a second.
Hello, sir.
Yeah, I finished my lecture. Any queries or anything you have, we can just ask. They can ask.
Hello.
If you have time, they can ask some questions. It depends upon you. You can just announce that. If there are any queries, I can explain.
Hello.
Hello, sir. Can you hear me, sir?
Yeah. It was a nice lecture. Now I ask, if the participants, if you are having any doubt, you can ask me. You can ask him directly, or otherwise you can post it in chat box also. Pranesh, you can stop presenting so that you are visible. You will be visible. Like, yes, sir. Any questions, participants? From participants' side. Any questions? I'll give just another 2 minutes. Then we'll go to the next session. Next session is feedback session, because by 11 to 12, the final session will be there from Dr. Sridhar, Director of School of Engineering from MIT University, Gurugram, Delhi. Delhi NCR, I mean, not exactly Delhi. So, and in between, you are required to give me the feedback. We want to have a record of that. So for that time, I'll give you 2 minutes. Otherwise, I'll ask